Uh, so this morning or this afternoon, we have a guest lecture from Dr. Watari and from Ms. Huang. So I just like to introduce Dr. Watari and Huang just briefly. So I will, it might be myself, I will present just a quick presentation regarding our works with Watari and Dr. Watari and Huang regarding the biological wastewater treatment on the textile waste. So just briefly the introduction of Dr. Watari. So Dr. Watari, now he is the assistant professor. It might be, I don't know, hopefully you are still, now is still the assistant professor. It's in the Nagaoka University of Technology in the Nagaoka, Japan. So he's working a lot on the biological wastewater treatment, and he visited Indonesia many times, actually before COVID. So I think almost I think in a year it's meant a number of times we visited Bandung, and then so we published together with Dr. Watari and also with the Professor Yamaguchi regarding the biological wastewater treatment on the textile waste. And Huang is doctoral student in the Nagaoka University of Technology, Nagaoka, Japan, and currently he is working with Professor Yamaguchi and also with Dr. Watari. So things are no further ado. I would like to Dr. Watari to present your presentation directly by yourself. So things are could you share yours?
Yes, Dr. Tjandra, thank you so much for your kind introduction. So today we would like have a lecture about the textile wastewater treatment. At the beginning, I would like ask you to Miss Fun to talk about the basic knowledge about textile wastewater treatment. Fun-san, please start your lecture.
Yes, thank you so much for introducing me. Now I will share my screen. Did you see my screen?
Yes, yes.
Okay, thank you so much. Okay, good afternoon, everyone. My name is Huong. I come from Vietnam, and now I'm following the PhD program in Japan. It's truly an honor for me to be here today. I would like to express my sincere thanks to the Professor Tjandra for giving me the opportunity to share with everyone a little bit about the research we have been doing in Japan on textile wastewater treatment. I hope we all today will have a nice and warm talk. And now I would like to begin my presentation. Today's presentation will be divided into the 4 parts. Part 1 will give an overview of dyeing wastewater. This is followed by a short summary of the strengths and weakness of the current treatment methods. In the third part, the anaerobic aerobic process for the dyeing wastewater will be introduced. Finally, I will bring to you some remarkable results of our textile dye wastewater studies completed in Japan to date. Now, let's start the presentation with the first content. The first question is, how much do you usually spend on clothes each month? According to some reports, besides the major spending such as housing, transport, or healthcare, about 3 or 5% of monthly spending of American, British, and Japanese is on clothes and footwear, of which the 90% usually come from clothes. It's so that although not a human daily needs, the fashion and apparel industry is still an important part of human life. That is why this industry contributes 1% of global GDP and still tend to increase every year. Asian countries are the place where this industry is very developed. In India, this industry contributes 2% of the national GDP and 12% to export earnings. Meanwhile, that figure for the Sri Lanka is 6% to export to the national GDP and 40% of total export in 2020. However, in reality, it is one of the largest water-consuming industries in the world. And according to the World Bank, this industry contributes up to 20% of the total global industry wastewater. Now, let's move on to the next slide to find out why. Although it depends on the fabric, overall, to make the 1 tons of fabrics, the 200 tons of water need to be consumed. In other words, the 1 kilogram of fabric requires 200 liters of water. Here you can see the stage of the dyeing, in which the most water-consuming stage is bleaching with 38%, dyeing with 60%, and finishing with 15%. Of all these stages, the dyeing process is our most concerned stage because this is the main source of many dyes and cause a highly color intensity in the effluent. Let's take a look at dyes a little bit. There are 2 main classifications of dyes, by application and by chemical structure, as you can see on the slide. Reactive dyes are the most commonly used dyes in cotton, yarn, and other cellulosic silk painting, and etc. because of their wide range of color and brighter shade. When classified by the chemical structure, the color group is often used to name X by. The bar graph shows the contribution of the azo dye to X dye type in the pie chart. As you can see from the graph above, the azo structure contributes 50 to 95% of the dye needed. In particular, 95% of current reactive dyes as azo dyes. In other words, azo dye as the largest group of the synthetic with the contribution of the 16 to 70% in the total dyes used today. So our research focus on these types of dyes. Let's try to consider the structure of this dye. Here is the typical structure of the symmetrical azo dye reactive like fire, which is used in our research as well. Structurally, the azo dye chemical structure is represented by a backbone. The also grown with the role of the shifting color and influencing dye solubility function, water-soluble groups, and chromophore, the most important group because the color of azo dye is determined by the azo bond and their bonds with chromophore and auxochromes. So why do the dyes attract attention both in terms of application and environment? Let's have a look at the dye process of sulfonated azo dyes. After initial process, azo dye go into the dye bath. Here we have the fiber like cellulose. After that, the 50 to 80% of dye stuff will connect to the fiber via covalent bond to make a color for your clothes that you're wearing now. Covalent bond will give a longer color finish than other binding force like van der Waals, so the azo dye become more popular than other. However, where will the remaining 20 to 50% of them go? Also in the dye path, another reaction will also occur, which is a hydrolysis, and the competition between it and covalent reaction to cellulosic fiber lead to a large amount of highly colored water being washed out into the natural environment, causing the serious environmental issues. And he says we need to treat this before it's discharged to environment. Currently, the physical oxidation and biological methods as the available technology for the treating dye wastewater. Here is the short summarized summary of some advantages and disadvantages of the current methods. In general, the problem with the physical methods involve the generation and regeneration of sludge and low decolorization efficiency. Meanwhile, high operational cost and formation of the toxic byproducts are the common issues with the oxidation method. Biological process sometimes stands out as a more cost-effective and environmentally friendly alternative to the textile wastewater treatment. So let's get to know more about the anaerobic aerobic methods. Sequential combination for the textile dyeing wastewater treatment has been reported since the 1990s. And so far, this is still the most logical route for the biological treatment of textile dyeing wastewater. This process begins with the adsorbate cleaving with the help of anaerobes and producing different aromatic amines. These compounds contain the benzene rings, which can be toxic to the nature and humans. So, aerobic followed in the role of the total mineralization of the compound, known as detoxification. That is the main concept of anaerobic aerobic treatment of azodized wastewater. In more details, the decolorization process is adsorbate cleave process, which involves the transfer of the 4 electrons to the adsorbate. In other words, the decolorization process of azodide essentially is an electron reception process in which azodide is a final electron acceptor, and the main source of electron donor for this reduction is from the decomposition process of another organic compound called assisted in dyeing wastewater, which can be a starch degradation, for example. At present, the aerobic treatment of aromatic amines and dye decolorization intermediate is also being studied, but encounter many difficulties because of the richness of intermediate products and the complexity of the industrial textile dyeing wastewater. Currently, our studies in Japan do not go into this issue, so I will briefly summarize a little bit this process based on some previous study. In this process, there may be 2 processes in the aerobic reactor that scientists have reported for this compound. The first is a mineralization by aerobes. This process usually requires the enrichment of a specific group of microorganisms. Several groups of aromatic amines have been shown to be aerobically degradable. However, the sulfonated groups are often difficult to aerobically degrade due to the hydrophilic nature of sulfonate groups, which interfere with the membrane transport. Another process you can see on the slide is a self-oxidation or auto-oxidation. Aromatic amines with the orthosubstitute hydroxy group are very susceptible, very easy to oxidation. Many aromatic amines such as aniline, aminobenzidines, or naphthylamine was found to oxidize to the dark color polymer with a low solubility and can be removed from the aqueous phase. Overall, this is still an interesting but complex process, and we will likely study in the future, maybe. On the slide is a summary of the several previous research about the anaerobic aerobic process for the dyeing wastewater treatment from the 2006 to this year, 2021. In general, this is a promising process for both organic and color processing, but it is a time-consuming process as well. And sometimes the color processing efficiency is not actually favorable, especially for the anaerobic process when the volatile fatty acids was accumulated. Now, I would like to introduce you a little bit our research about the dyeing wastewater treatment by anaerobic aerobic process. In this research, we choose the anaerobic buffer reactor and Delft low hanging sponge reactor for artificial textile wastewater containing the commercial auto dye named the halozone reactive black SLR almost on the reactive black 5 supplied by an Indonesian textile factory. The reactor was operated under about 23 hours of HRT hydraulic retention times and over the 120 days continuously. In this research, the compartmentalized structure of the ABR allows the microbial group to live under their favorable condition and avoiding hydraulic, organic, and toxic shocks, which can seriously affect a single compartment reactor. Especially, the ABR was designed with up and down line separation at two distinct columns instead of using buffers. This allows the ABR workspace to be maximized, and wastewater can be treated at both the up and down movement in the reactor instead of just the up line as in the traditional ABR. For DSS, this reactor can run without any external aeration. Moreover, sponge can have both internal anaerobic and external aerobic zones that can both have cheat the residual color after ABR and perform roles as an intermediate compound aerobic reduction. Here, I show some remarkable results that we already got. In terms of the treatment performance, in general, the system has a demonstrated potential in the treatment of textile dyeing wastewater. The total efficiency of the whole system was 80% and 50% of COD and true color, with the processing time of the 23-hour total. The COD and color treatment mainly take place in the ABR, more specifically at the first column. Also, in this first column, we discover the predominance of some microorganisms that have been reported to participate in dye degradation, such as Clostridium centrifuge or SRB group, the sulfate-reducing bacteria. Detail of this study can be found in the first paper that I will attack on the last slide. However, the main problem of the study is the movement of the slot caused the instability of the system and lost its original intention when designing the system. And because of the ABR promising COD, ABR have the promising ability for the treating COD and color processing. So we continue to do more in-depth research on the ABR. That's why I show you the second study. In the second study, with the goal of immobilizing microorganisms to differentiate the function of each column, we added the polyurethane sponge to each compartment as a biocarrier. The operating condition of the system was similar to the mentioned study, but the HRT and input COD was changed to evaluate the stability of the system. The results show that the processing performance was superior to the ABR without sponge, with 65% and 83% compared to the only 42% and 60% of the dye decolorization and organic degradation under the HRT of only 14 hours instead of the 18 hours. And volatile fatty acids did not accumulate in the system. And ABR profile so that the addition of the porous sponge to the ABR has a well-fixed group of microorganisms in each column, contributing the great stability in the processing efficiency when we change the HIT and organic load. About the microorganism analysis, you can see the heat map and the PCR analysis on the slide. Here is the most prominent 22 genera of the SSABR with a maximum abundance defined in the one of the column of the 0.8%, more than 0.8%. Microbial group capable of participating in the dyeing process was detected at a greater rate. And interestingly, in this research, methanosacina and zeobacter was detected prominently and tended to have a proportional distribution with each other in each columns. This may reveal a symbiotic relationship between the two species and have the methanosacina to live well. And we began to doubt whether or not the symbiotic relationship or syntrophic relationship contribute to the dye processing. And in addition, in the PCA plus, so that the sponge can allow the important microbial group be retained and functionally differentiated within the egg column, so that the metabolic activities can proceed smoothly even under extreme conditions. And this study has also been published. More detail can be found there. So in general, textile dye wastewater needs to be treated properly before being discharged into the environment. The expansion of environmentally friendly methods, such as the biological methods, can have some countries with the textile dyeing as a key industry can reduce the financial pressure when trying to handle it. The anaerobic aerobic combination biological methods has many potential to completely decompose textile dyeing wastewater. However, after researching the anaerobic system for the textile dyeing wastewater treatment, we found that the common challenge of the azodye anaerobic treatment include the long processing time because dye decolorization normally depends on other organic degradation process, and unfortunately, it is often time consuming. Secondly, the toxicity of dyes and their intermediate metabolite can inhibit the growth of some microbial group, especially the sensitive microbial group like methanogens, and low concentration of biodegradable compound can lead to the lack of carbon source for the dye decolorization. Therefore, in an effort to completely treat the textile dye wastewater, we are trying to overcome all of these problems. And here's some of the publication. If you are interested in it, check it out. So thank you so much. That is all of my presentation. Thank you so much for your kind attention. Now my professor will introduce more interesting details about the real ABR DSS for the textile wastewater. Let's follow it. Thank you so much.
Thank you, Huong. So I think so. Okay.
Okay, can you see my slide?
Yes.
Okay.
Yes.
Yeah. So thank you so much, Miss Huang, for explaining the research. So in my presentation, I will talk about the actual application to the industry for textile wastewater treatment. So before starting my presentation, I little bit introduce myself. I am Watari, and I am belonging to the Department of Civil and Environmental Engineering in the Nagaoka University of Technology, Japan. And also I worked in Vietnam more than 6 or 7 years. So I have a position in Hanoi University of Science and Technologies. And previously, I worked in the UNESCO IHE Institute for the Water Education in Delft, Netherlands. So I saw that the Dr. Eldon will present in the next seminar. So I want to know that he's talk too. And also I little bit want to introduce my university because my university also open for the Indonesian student. So my university is second ranked technology university in Japan. Maybe ITB is the first in Indonesia, and we are the second ranked technology university. And also we are number 9 SDGs number 9 gold Hub University. The number 9 is industry, innovation, and infrastructure. So we are our research also belonging to the achieve this goal 9. And now we have 10 Indonesian students in my university, and we also have a MOU between the ITB. So we are really welcome to the Indonesian students to come to study in Japan. So please consider it. So now let's start my presentation. So I cannot move to the next slide. Okay. So as Ms. Poon told me, the textile wastewater is like this. It always discharges the high temperature, sometimes more than 40 degrees Celsius. And also large amount of the wastewater is discharged. In case of Japanese textile factories, 1 million cubic meter wastewater is produced per 1 day. And most difficult things is a large water quality difference. I will show that about this one, but this is one of the difficulty to apply the biological treatment system for textile wastewaters. And also the wastewater contains sulfide and also toxic chemicals, and sometimes also contain the heavy metal like copper or coppers, something like that. And also azo dye can degrade only the anaerobic condition. Therefore, so this is a difficult wastewater for treatment. This is a picture in the textile wastewater factory in Indonesia, and this is a photo in the stadium river in Bandung. Maybe you always see like these rivers. So therefore, the textile wastewater is a major pollution source in river. So in order to treat these wastewaters, we are applying our wastewater treatment technologies. This technology is we use a sponge, and this is developed for low-cost sewage treatment process for the developing countries. Actually, my research group developed this system and applied to the India or Egypt, Thailand for the full-scale sewage treatment. And this sponge can retain the large amount of the biomass. Here is a SEM image. This is the pure sponge carrier, but after operating, the biomass living into the sponge carrier. And also, this reactor is treating filters, and the water comes from the top of the reactor. Then the wastewater is dropped and dropped and dropped. During that time, the air, especially oxygen, is dissolved into the waste in the water. Therefore, this reactor can achieve the high oxygen transfer without aeration. And also, in this sponge carrier, they live many kind of bacteria, fungi, or something, and they can eat together. Then the DHS reactor perform the low excess surge production. This is the comparison when treated domestic sewage. DH is only 0.06, and the activated surge process is 0.42 to 0.46. So for applying the textile wastewater treatment, DHS reactor is maybe good because in this sponge carrier, as you can see in the surface, it have oxygen, and if going to the inside the sponge, the DO is going the lower. That means inside the reactor, anaerobic bacteria can survive, and the surface aerobic reactor can survive. So we can make one reactor in one anaerobic aerobic reactors. So our idea is a specific aerobic anaerobic zone in the sponge media can be effective for the dye degradation. So in this study, we are applying this reactor for treatment of unactual textile wastewater discharged in Japan. This is our experimental experiment. We bring the textile wastewater from the actual factories. Then the wastewater feeding to the DHS reactors. In this research, we focus on the effect of the recirculation. Recirculation means that a one-time treating wastewater is then collected. This one bring back to the influent again. Then the wastewater can treated several times. Then we try to improve the treatment performance using recirculation. This is an operational condition. So this is the information of the textile wastewaters. The factory is located in the Nagaoka city in close to my university. And this wastewaters contain the wastewater produced from dyeing textile processing process, bleaching process, and final washing process. The characteristic of the wastewater is here. Comparing with Indonesia, this is, I think, low strength textile wastewater. This figure shows the total COD concentration and the color during the experimental payload. Right side shows a picture of the influent and effluent, and also this one is influent and effluent. As you can see that for the blue color, we can get a very clean water, but in case of red dye wastewater, a little bit become clear, but not much clear, not much clear waters. So this is a summary of the effluent quality in the DHS reactor. All operational run can achieve the discharge standard in Japan. But the remarkable thing is in Japan, we don't have any standard for the color. So anyway, the DHS reactor can be applicable for the direct wastewater treatment from this research. Next figure shows the total BOD, total COD, total nitrogen removal efficiency in each operational run. When during the all operational run, we observe the high organic removal efficiency. That means that the DHS reactor have a great performance potential for the organic removal in this textile wastewater. However, the nitrogen and the color removal has a large difference by the operational method. I mean, the effect of the effluent recirculation is bigger. Generally, HRT extension increases process performance. However, comparing the HRT 4 hours and 8 hours, the 8 hour is worse. This means that we are thinking that the effect of the DO. So extension of the HR leads a shortage of DO because the water is moving very slow. And this figure shows DO profiling in the sponge reactors, in the sponge. You can see when we operated the HRT treatment times 4 hours, we have much enough DO in the sponge carrier, but we operated at HRT 8 hours. As you can see, the DO is shortage due to the low flow rate and the low retention time in the sponge. Therefore, the ratio of anaerobic and aerobic zone is very important for nitrogen and dye removal. So this is a dominant the result of microbial community data. The dominant dye degrading bacteria is very different between the with effluent recirculation. This is without effluent recirculation, and this side with effluent recirculation. The main dominant bacteria in lung 1 is Acinetobacter. This is an anoxic azodide degradation bacteria. And after a change to the operational condition, the dominant bacteria is Cyanobacter. This is aromatic hydrocarbon degradation bacteria with a low DO. Therefore, the dominant azodide degrading bacteria is changed in the DO concentration. So conclusion of this study is that the single DHS reactor can perform the high organic and nitrogen color removal in actual textile waters. The ratio of anaerobic and aerobic zone is very important for dye removals. That means the effluent recirculation is effective for the nitrogen and the color removal by enhanced oxygen transfer. And dominant dye degrading bacteria was corresponding to the DO concentration. So from this research result in Japan, we try to apply to the Indonesia to these technologies. This is actually I think everybody knows about the current stats in the Stream River area. I saw that this report, they show that 838 industry were categorized into the 6 types, and the water consumption, like surface water, groundwater, was providing the waste removal agencies. Pollutant concentration in industrial effluent is assumed in table 8. And loading was calculated by using water composition, concentration, percentage of industry with wastewater treatment and removal efficiency by WWTP. Basic scenario was adopted. As you can see, the textile wastewater is compared with other wastewaters. It is low. However, the main industry in the Stream River is textile wastewaters. This is the total water demand in the Stream River basin for industry is 230,000 cubic meter per day. And the major part of the industrial wastewater use, on average, 84% is by the textile industry in upper Stream River basin. So to improve the Stream Rivers, measures for the textile industries must be implemented. So in order to solve this problem, we created a new research project to the textile wastewater treatment funded by Ministry of Environment in Japan. The project member is a Nihon Seido consultant in Tokyo and also Sankey Engineering in Tokyo and our university. Now, this project is conducted in 2019 to 2020. And we are trying to apply our technology, ABR-DHS system for an actual textile wastewater in Chimahi. So this is information about a textile factory where we applied this. The name is Pangejaya Factories. The factory is operated 221 days per year, and operation time is 24 hours. And then employed to the 700 persons as an employee, and the major products is cotton, rayon, polyester, nylon, and TC. The production is 220 tons, and the manufacturer's processing is sorting and bleaching, dyeing, reduction, cleaning, soaping, and finishing. The important thing is this factory is not have a desizing process. This is very important because if you have a desizing process, it's wastewater contain the organic, then easy to treat. But in this factory, didn't include this desizing process. The water discharge is around 1,800 cubic meter per day, and this is tables, this figure shows the current wastewater treatment system in the Pangja factories. The influent go into the equalization tank, then filtrated by the aeration tank, then go into the clarifiers. After that, they are the DCA, decolorization agency, and PAC and polymer. Then finally discharged. And after since July 2019, they installed the DAF, dissolved air flotation system in the factory. So in this project, we installed the pilot scale ABR DHS system, and this figure shows our installed systems. To the beginning with, half of ABR tank was filled with excess sludge from the aerobic tank, and ABR was sealed to keep the aerobic condition. At the beginning, we cultivated anaerobic organism for 6 months by running the wastewaters. And we also cultivated anaerobic organism for 2 months in the DHS reactor. So this is a concentration in the low waters, and also target concentration in the final effluent are shown below. The target value meet with a low regulation apply for the industry in Stadium River Basin. As you can see, maybe one arm in the color, I think, but the average is 2,200, but you can see maximum is 27,000 and minimum is 250. So they have a very big variation. And also BOD and COD also have big variation. So we start the experiment from the June 2019. The dosing rate of decolorizing agency was reduced by 45% compared to in the industries. Dosing rate of polymer was same as that in the industries, and dosing rate of PAC was same as those in the industry, 1 liter per cubic meter for round 5, and it was sit higher than those in Pangja for round 4. So this is a figure so the color and the COD during the experiment. After dosing, the DC and the PAC and the polymer started in the round 4 here. The COD is finally met in the target 155 milligram per liters. Here is evidence COD data. However, it was quite close to the target. Color also. Sometimes we can meet the discharge standard, but sometimes exceed the standard. It is depend on the influent characterization. So the reason why COD concentration in the final effluent sometimes exceeds in the target is, of course, our pilot scale system is very small, and water loading is on the clarifier is satisfies the standard value, and also mixing the chemical as water is not good. Therefore, we will bring the waste water from the factory, then we will do the table test also. But this figure shows the result of table test. Sorry, this is the Japanese, but this y-axis is the COD concentration, and x-axis is the DCA dosing rate. And if we do the good condition, we can achieve the effluent standard from this table test. So from this experiment, we obtain a similar data, and we analyze that data. Then we can get the estimated sludge waste, comparing with our technology and CAS and chemicals and the DAF and CAS systems. In sludge waste was approximately 0.67 kilogram per cubic meter treated in the CAS and chemical system in the industry. In this experiment, excess sludge is discharged from the clarifier with volume of 55 liters once a week. TSS is discharged in discharge that was determined. Sludge waste per water treated was estimated as follows. This is a calculation equation. Then we obtained the 0.049 kilogram cubic meter treated water when assume that the water contains sludge waste is 70%. So the compare with this system and the current treatment system, we expected we can reduce the sludge 75%. So here also we are calculating LCC in 15 years and also greenhouse gas emissions. And also in the Shimahiriba Basin land area is now, land is very expensive. So how can we reduce the treatment plant area? We calculated. LCC for ABRDH system is lower, those CAS plus chemicals, but it is a little higher than those DAF and CAS system. However, the ABRDH system is superior in terms of greenhouse gas emission and also sludge waste and land area. In proper system, reducing effort of the green GHGs and sludge beyond compliance is considered when rating the company. So company may get a green rating on the proper if this system installed. So this is the take-home message from this my lecture. The characteristics of the textile wastewater is largely different in each company, each factories. Therefore, understanding the textile process is very important, especially with or without desizing process is very important because the wastewater contains the easy degradative organic or not is very, very important for the biological system. And application of the combined anaerobic aerobic biological treatment system has a great potential for reducing the operational cost, also excess sludge and greenhouse gas emission. So currently, now we are improve the treatment. We are researching about how to improve the textile wastewater treatment, even the wastewater didn't contain much organic. So thank you so much for listening, and we are very appreciated for cooperate with Tjandra Sensei to do this project. Thank you so much.
Thank you, Prof. Watari. And okay, things. Just I will present briefly our. So I will present briefly just briefly of our paper with my student also working on the biological wastewater treatment, and also Dr. Watari and Professor Yamaguchi also as a co-author of our publication. So that one is a combination between the anaerobic membrane bioreactor and DHS down flow hanging reactor has been explained by Dr. Watari. So that's just briefly. I will talk briefly. So that one is a work of my student Choi Rudin, and also with the other student, and this one is about the anaerobic membrane bioreactor. So that one is using the hollow fiber membrane, and then the feed is not the real wastewater, but it is using the synthetic one, and also with the RB5, so black ASO black 5. So that one is the feed, and then pumping to the anaerobic membrane bioreactor. So that one is the feed, and then later on put it in the DHS. So that one is the the example of the color from the inlet, and that one is the outlet of the anaerobic membrane reactor, and then that one is the outlet of the DHS. So the DHS has been explained by Dr. Watari. So that one is the new before applying the waste. So that one is the after. So that one is basically we are using a different HRT. So that one also different fluxes. So that one, so the flux is relatively low, between 2 liter meter square per hour until 5 liter meter square per hour. So that one, I will show you briefly that anaerobic membrane bioreactor has been a potential as well for anaerobic anaerobic system. Of course, that the performance is relatively better, but as you may aware, the MBR will be have some other disadvantages about the biofouling. So you can see that the color is very good. So most of the color has been reduced in the anaerobic membrane reactor. So that further down to the DHS. So that one can meet all the color, all the BOD, all the COD is can meet the standard. So that one is from just to say that there is a bit increase on TSS because of after the DHS because of no separation. So that one is easily to reduce the TSS, just have a settling tank after the DHS effluent. So I think I would like to say that although it is only for synthetic waste, but anaerobic membrane bioreactor combined with the DHS has been a very a good performances. But although the anaerobic membrane has been a challenges in the, I think so for the, I will skip the microbe. So the conclusion is the falling. The falling in the membranes relatively rapid, especially in the higher membrane fluxes. But the performance, even with the RRC of the 12 hours, has a very good performances. So I think, but we have to do, we have to use and to prove if we use the real wastewater for in the future. So I think it might be in the future my student will work on the real wastewater. So I think that one is the additional research of my student working on the biological wastewater treatment. So I think we will move on to the discussion. I think the Huang has been presented the work, laboratory works, and also myself using the different combination. But Dr. Watari has been presented the real wastewater using the real textile wastewater. So I think if you have a question, it might be Arik or the more. Can you help us with the if there's any question or Nida? Please, Nida. Okay.
Okay, this is the first question.
Okay, Nida.
For Ms. Huang, it is possible that use plants for textile wastewater treatment?
Oh, sorry.
If can, what kinds of species plants?
Oh, you mean that using the plantation? Oh, that
Yes.
one is like a wetland, something like that. Okay, probably Huang or Watari would like to Dr. Watari would like to address this one. Is there any possibility to use the plantation to treat the textile wastewater treatment, textile waste water?
Yes, I think there one important thing is how to feed the oxygen source to the wastewater treatment. And now I and my colleagues are researching about put some wood chip in the bioreactor. Then if put that one, maybe gradually the bacteria eat the wood chip for getting the organic source. So that's why I think it is possible. But in case of textile wastewater, I never try to do that. So let's research together about that.
And I think maybe can, because like some, how say, if we use living plants, I'm not sure, but how say some plant can how say can become the natural base materials of the low hanging sponge, you know, the sponge. And sometimes we can use some space, some plants, and how to say, treated it and create to become the how to make it to become the sponge, the spore sponge. Our lab also have the one student, PhD student, how say, she also published one paper about the natural based materials. However, the problem is, you know, like inside the anaerobic reactor, we have the microorganism. That's why the problem is how we can treat the material for maintaining for a long time. Yeah, because sometimes microorganisms can eat the plants, right? And that is my answer. Thank you so much for your question.
Yeah, things have, as been mentioned by Dr. Watari and Huong, it might be possible, but if you are looking to the COD and BOD of the textile waste, the phyto or phyto, how you spell it, is a rather low process. So I think due to, like in Bandung, you have a very limited space. I think the phyto remediation might be not the option for treating the textile wastewater textile waste. If you have a rather large space, it might be possible. I think that was the additional comment from me. So then next one, Ida. Yeah, I think the same, right? So what do you think to combine the combination of the study method with the constructed wetland, if the land is available? It is financially effective, or it's better you enhance the existing one? Probably, I think so. Please, Dr. Watari probably can address this one, or
Yes, actually, I didn't much. I don't have much knowledge about the wetland. But is it possible to treat the textile wastewater in wetland?
Yeah.
Is it? Can I see?
Yeah, I agree that I think the combination of this method with the wetland, if it is the land possible, if the land available, I think financially it will be one of the choices. But the I think the key is the land. So if if we have the land, because the wetland is very good for the nutrient removal. It might be good for the heavy metal removal. I think it's a good idea, but the key is we have available of the land. So if you Hong, you would like to have any other comment?
Yeah, this one, yeah, I have no comment. So Yeah, so you can,
Yes.
thank you so much for the question. You can refer the Watari Sensei and what Professor Watari and the Tjandra
Okay.
for the answer.
Okay, thank you. So I think the next one it is to me, right, about the MBR. Yeah, I think so. Usually, anaerobic tank has low slot generation and mainly process. Yes, it's correct. So that one is possible. So the anaerobic membrane bioreactor is now one of the hot issues. So that one is you can search and you can see that now a lot of publication on the anaerobic membrane bioreactor. It's true that anaerobic membrane bioreactor is mainly for the dissolved uh, substances. So for the if the test as or the slot or the solid the suspended solid is too high, it is not suitable for the MBR. So you are correct. So that one is the anaerobic MBR is hot issues now. So there's a lot of publication on that subject, and it's true that the anaerobic membrane bioreactor is for the more in the dissolved substances. I don't know, Dr. Wata, you have experiences with the anaerobic MBR? If you have, you may. Okay, so that we may move to the next question, please. I think that one is to Huong and Dr. Watari.
Yes, please.
Yeah, I think so. Oh, so what the employment of strong material in the HV? Oh, probably. Yeah, in the probably you explain about the HS first. So then, what will be the possible future application in the research? Please.
Yeah.
So it might be you explain about the DHS. What is the DHS all about, and then what is the possible research in the future?
In the future, yes.
Yeah.
So I see. Sorry, I will share my slide again.
Okay.
Yes, this is a DHS reactor.
Yes.
And it's kind of treating filter. And normally in treating filters they use a stone or the plastic or something, but this time we use a sponge for biomass retain carrier. Then the interesting point is this biocarrier can retain the maybe 20 times higher bacteria inside the sponge carrier. Then we can perform the high removal efficiencies. Then in the question, sorry, I'm not 100% understand this question mean cultivated bioreactor means about the microbial communities.
Yeah, I think so. It might be the next question regarding what will be the needed research in the future.
Future, yes.
Yeah.
Yes. About that point, this is this technology is almost we completed the research, and next topic is how to make this one with cheap price to apply to the industry. Actually, this sponge carrier is quite expensive because we make a sponge and put by hand into the plastic carrier. So the next our research is how to how to make a machine to make a more sponge media with effectivity. Now I'm thinking that.
Yeah.
Nguyen-san, do you have?
Yeah. What is the future research for the DHS? If you have any other comment or any idea?
Yeah, and besides the how say, normally the main content of DSF is a sponge. So besides this, using it as an aerobic treatment, how say the post treatment follow the anaerobics, we also use the sponge as a good carrier for the anaerobic treatment. We were very considerate about some material like conductive material or magnetite. They can, how say, improve the metabolism of the microorganism. And we also know the porous of the sponge is very good for the microorganism to attack too. So in the future, we can find a good way to combine the sponge with the magnetite in the future for the anaerobic treatment process.
Oh, with the magnetite. Oh,
yes.
So you put the magnetite into the sponge. Oh, great.
Yes.
Okay. For the next question, please. So you have.
Okay, next question is about the exoskeleton, right?
So, Nida, what is the next question, Nida?
Okay. Sebentar, Pak. This one. Can Mr. Watari please explain how this large amount of ABR-DHS method is much lower compared to the CIS and CIS chemical methods?
Yes, the difference is that before the chemical treatment, the DHS effluent water quality is better than DAF effluent. That means the water quality difference means if other chemicals, the difference of the water quality directly affect to the sludge amount. I mean if the COD is 50 and the 200, the difference is 150. And at this moment, if other chemicals, 150 milligram COD become a sludge. So therefore, not only ABR DHS reactor, in case of biological, if apply the biological wastewater treatment, it is very important for treated water as much as possible. Then the excess sludge amount getting lower. Is it correct answer?
You have explained that one because ABR and DHS the sludge production is relatively low. It's correct, right? So from DAF and CSS with the DAF will have use chemical as well. Sometimes you have to use chemical. So that one, and also of course with the CSS and chemical also produce the chemical. So I think why the EBR and the HS have the smaller slot production, because totally it is the biological treatment, and so that one is it is the reason why that one the lowest one. So that I think so that that's I think the next question is it's supposed to be that one. The question is using the just only biological treatment, can we match the Indonesian standard or not? What Dr. Watari, as you have been mentioned earlier, please.
Yes. Actually, for the color is impossible color is difficult to remove, totally remove in the biological system. So chemical treatment is necessary, I think.
Yes.
But after, yes, please.
Yes. So so that one is according to the research by Dr. Watari for the real wastewater, not for the synthetic one. For the real wastewater, Dr. Watari has been mentioned that the problem is to meet the color standard. So the color with the 200 PTCO is difficult just only using the biological treatment. So at the end, still have to use the chemical treatment. It's correct, right, Dr. Watari?
Yes.
Yeah.
And I think like maybe now we cannot match the safe concentration. However, we try to minimize the chemicals that we use. Is yeah. So if we can increase the efficiency of the biological treatment, we can decrease minimizing the chemicals that we use in the post treatment. I think so. I hope in the future we can find a good way to biologically completely the distilled wastewater.
Okay, thank you. So with the good biological treatment, we need just only a little chemical at the end
Yes.
to reduce the color. Okay,
Yes.
thank you. So that what is the average life? So the question is relative. Say it. Oh, so that is there any is the down hanging sponges should be replaced or can be used for what is the lifetime of the DHS? Please.
Yes. So in our experience, now we are operating the DHS reactor for treating the domestic sewage in Thailand. Currently, now we operate in approximately 15 years.
15
And
years.
during that time, we never changed the sponge. So
Ah.
now I can say the 15 years, but maybe more, I think.
Okay, so already 15 years use the DHS without any replacement, right? Okay,
Yes.
great, yeah. Okay. Uh, uh, so that one is the question about DHS. How make sure that it is the professional with an anaerobic, anoxic, aerobic zone while in use. So I think you already having the data, right, about the DO
Yes.
profile.
Yes.
What is the key for the please
Determine the media emission.
dimension and yeah, this probably that one could we have to so the size is already correct or not, or we can
I
reduce
see.
the size or can enlarge the size or that
Yeah.
one is already
Yes. So that is very important. Now we are this diameter is 33 millimeters. This is we designed the basic based on the sewage treatment plant data. So for yes, I think we need a optimization for the textile wastewater treatment. I think in the washing the how often sorry
do you need any wash
uh
to the HS? I think no, right?
no yes
No wash, but
yes
it's regarding the because the DHS there will be aerobic in the outer layer, and then might be anoxic, and then an anaerobic inside the media. Is there any proportional zone to treat the waste that the aerobic should be 10% of the sponges, or anaerobic should be certain percentage. So is there any possibility to control the proportional zone of uh, the sponges?
Yes,
Is there
that
any
is
possibility?
very, yes, we are, actually, I researched about this in Netherlands, in IHE. We try to cultivate the Anamox bacteria inside the sponge. In the surface, we try to cultivate the nitrogen bacteria, but currently, very difficult. But very interesting, I think. My
Yeah,
college, who come from Brazil, he now making a model for optimize the sponge carrier diameter. Yes, that is very important point, I think.
yeah. Probably Huang, so you have any idea or is any comment, further comment?
Yeah, I think this one is very interesting. Sometimes I also ask myself how to control the which area is anaerobic, which area is aerobic, which area anaerobic. And how to say, like, I think how to say sometimes the direction that the how to say direction of flow is a very important to shape the which area is anaerobic, aerobic, or anaerobic. Maybe we can try to find
Yes.
more in detail in the future. Thank you so much for your lesson.
Yeah, great. So that uh, the next question is regarding uh, the wish. That's where instantly will come from the. Yeah, I think so. Your experiments in uh, Bandung is only from the textile factory, right, Dr. Watari?
Yes, yes, but we already applied to the another wastewater, like of course fish meal processing wastewater in Bali, and
Oh,
also natural rubber wastewater in Vietnam and Thailand,
uh-huh.
and molasses wastewater in Thailand also. So yes, we have many experience about to apply to the another factories.
Yes. Yeah. Okay. So that in Citarum River is only textile, but the experiences from in Bali and Vietnam, Thailand has been using for a different factory. Uh, is there any other, or is there any experience to use for the paint factory waste from the?
Uh,
No,
paint is difficult. Yeah, we want to try it, but have to consider how can regard it by microorganisms.
yeah, yeah. So that this method can be applied for other factors. I think Dr. Vartaris has been answered. So that has answered this one. So that used for the other industries. That has been applied for the uh, food industries and then other industry. So how the performances in for the other industries is good, or probably have sharing a little bit, Dr. Watari?
Okay, yes. Uh, for the fish meal processing wastewater, it is very good, and we can cover the methane from the wastewaters, and we can also operate the factory by using that methane gas. And in the molasses and natural rubber factory also we can get a good organic removal efficiency together with energy recoveries. But in those the industry, we also have to research about the nitrogen. Nitrogen is always high, especially fish meal and natural rubber. So now our the research point is how to treat the nitrogen in the wastewater.
Yeah. Okay, thank you. So I think the next question regarding the uh, has been using other colors, other dyes.
Uh, for this question, now we just only focus on the commercial dye stuff. from the Indonesia factory supplied. And it is almost a reactive like fires. And now in our new research, we use the original reactive like fire. Before applying to the another kind of dye like reactive blue 19 or reactive red 2. I know reactive red 2 is very, very popular. We want to confirm the degradation pathway of reactive black fire first. And yeah, and after that, we will try to expand the maybe the mix of dyes or other dye. So yeah, this is the answer. Thank you so much.
Okay, I think Dr. Watari has worked on the real wastewater, right? So the real wastewater is it's
combined a lot of
combined. Probably Dr. Watari already mentioned, but can you briefly about the result with the different colors?
Yeah, actually, I didn't know what kind of dye contained the wastewater. So, but the color in the wastewater is significantly affect the performance. In case of the Japan, the blue color is easy to degrade, but red color is difficult. That is my experience.
Yes, it's correct. So that it means that we need more research on the using a different color, and also has been addressed by Huong is a mixed color. So that mix also is another challenging one. But has been mentioned by Dr. Watari regarding the research using the real wastewater. So that one is basically red is one of the most difficult one to degrade it. Yeah, so
yes. And I sometimes I think I'll say the dyes it depends on the which kind of dyes. For example, the azo dyes normally is a harder. For example, the sulfonate dyes normally is a harder to treat than other dyes. So we choose the reactive black fire because it is the popular dye, and also it have some structure very hard to degrade. So yeah, so that's why I think in the future we will try to mix other dye and treat it. This is very important for the real.
Yeah, I think for the next one, I think probably we can briefly about the investment cost and also about the specific surface of the sponge media, please.
Yes, about the investment of this system. As I told before, the sponge carrier is actually very expensive. So that's why the compare with the conventional system, maybe higher than 1.3 to 1.5 times higher than a conventional system. But the compare with the conventional system like activated sludge, we don't need aeration or some operational maintenance. Therefore, the compare in the investmental cost, it is expensive, but the operational cost is very cheap. So the maybe 5-year cycle or some, I'm not sure how they calculated how to replace the investmental cost, but total cost is cheaper than conventional systems.
Yeah.
And specific about a specific area, it was 1.87 square meter per cubic meter. It's okay.
Yeah. Okay. 1.8.
1.87. Yes.
Okay. Okay. So I think that one is regarding. I think that one is for me. What is the main differences between DHS and MBR? So that one is a very deep. So DHS is more like a tricking filter. So MBR is more like so as that one is the like DHS is more attached growth. MBR is a suspended growth. So it means that DHS, the microbe attached to the media. In the MBR, the microbe is suspended, but the separation of the liquid or the water with the microbe is using the membrane. So that one is a different system. One is the attached growth. The other one, MBR, is more like suspended growth. So the microbe has been suspended in the MBR, but in the DHS, microbe is attached to the media. So I think probably we have run out of time. So but we still have a few minutes, so that probably the next patient is textile use. Okay, so that's one already answered. So the surface area is already answered. So oh, it's gone. So that's gone. I couldn't. Yeah. Some Takahiro you see the synthetic guy. Yeah, I think so. Please, probably Huong, you can because you are working on the pathway how the dyes can be degraded by the microbe.
Yes, as I said before, biological treatment of the azo dye will have the two kind of thing. The first one is anaerobic and other one is aerobic. Because we focus on the anaerobics, that's why we'll explain a little bit about the anaerobic. In the anaerobics, for example, now we already got the one microorganism who can secrete the azoreductase. Azoreductase is the enzyme, yeah. Azoreductase for the cleaving the azo bond. Yeah, and how to say, like the clostridium per finger can secrete the azoreductase, and after that, the azo dyes will go near to the clostridium, and after that, the enzyme secreted from this one can cleave with this azo bond, and also using the NADS from some redox mediator from the clostridium. This is microorganism can break down the azo bond for the decolorization. However, after that, we create the aromatic amines. As I saw in the one paper in the Nature, they said that after aromatic amines produce, some process like deamination or desulfonation by the lactase enzyme also included until creating the acid oxalate. Yeah, that is my answer.
Yeah. So that one is what the Huang has explained, that the synthetic dyes can break down by the microorganism using mentioned about the possibility of the enzyme working on the dyes. So that I think for the next question is regarding our next research project. So it might be so maybe after the COVID we will work together again. So, and also there's the question regarding the student willing to have to join either with me or with Dr. Watari. So you are welcome. So I think my student also, I think my prospective student also here is from India, Syed. So Bobby Syed also will work with me and also may join Dr. Watari as well. So after we are working here in Indonesia in IPB and then may join with Dr. Watari.
Thank you, sir.
So,
thank you, sir. I'm here. Yeah.
Yes,
hello, Dr. Watari and Ms. Huong.
Hello.
Great. So Dr. Syed is from India. He will join me in the next semester.
Yeah.
Nice.
Thank you so much for introducing me to Dr. Watari and Ms. Huang and all. I'll join Tjandra sir maybe in few months if all things is going to be okay. If the situation will be okay here and there in ITV. Yeah. Thank you so
Nice
much.
to meet you too. Thank you so much.
Same here.
Okay, I think I think one of the last question because we have run off our. So that is there any clogging issue on the sponges?
In case of until now, actually we don't have a clogging issue because surface we have a much microorganisms, then they can eat. But my concern is if directly applied to the DHS reactions, maybe textile wastewater contain some retained inorganic. So until now, we don't have a clogging issue, but in the future, maybe we will happen. But it is very easy to wash. So I think not a big problem about the clogging for this DHS reactor.
Okay, okay, thank you. I think we are around of time. I would like to thank to will be also strengthened in the future and they come again to Bandung. Okay, Huong we never been to Bandung, but we will welcome you to Bandung.
Yeah, thank you so much. I will try after COVID-19.